channel. In this video, we shall be looking at motion. What are the objectives of this video? At the end of this session, the students should be able to calculate the resultant velocity using simple example of motion of objects with one or two changes in direction. Show on a velocity time graph the motion of a body with uniform velocity, uniform acceleration, variable acceleration. Deduce the distance covered between any intervals on the velocity time graph. Deduce the three equations of motion from a velocity time graph with initial velocity and constant acceleration. Explain the terms used in the equations of motion. So let's look at some basic terminologies used in motion. Firstly is displacement. Displacement is defined as the distance traveled in a specified direction. It is a vector quantity. When we refer to distance, distance is a quantity that is not indicated with direction. It is a scalar quantity. It only has magnitude. While displacement is defined as the distance traveled in a specified direction. Speed. Speed is the distance traveled in unit time. It is a scalar if an object covers equal distances in equal intervals of time, then the object is said to have a constant or uniform speed. Say, for example, when an object moves from point A to point B, it moves a distance of 5 meters in 2 seconds. Then it moves from point B to point C, a distance of 5 meters for another 2 seconds. Then it continues to act like that. Then we say the object is said to have a constant or uniform speed. Velocity. Velocity is the rate of change of displacement with time. It is a vector quantity. Acceleration is the rate of change of the velocity with time. So let's look at the velocity time graph. Suppose the velocities of an object moving along a straight line are given by the following table of values for the first 12 seconds. For some of us that have boarded a tricycle or a motorcycle, we find out that at the part of the motorcycle, we'll find out that at the portion of the motorcycle where the driver controls it, there is a meter that reads the speed of the motorcycle. Based on what has been done, we find out that the unit on that meter or onto that device rather is in kilometers per hour. That implies that that is the speed of the motorcycle. But when we are referring to velocity, velocity acts it is indicated with direction. So when we speed and velocity are very related, they are alike, but what differentiates them is that speed is a scalar quantity while velocity is a vector quantity. So when we are talking about speed, we're also talking about the velocity. So that's it on that. So now let's proceed with the velocity time graph. Suppose the velocities of an object moving along a straight line are given by the following table of values for the first 12 seconds. So the velocity here 0, when the velocity is 0, the time here is 0. When it is 2, we have the time as 1 second. When it becomes 4, time 2. When it becomes 6, got 3. When it becomes 4, goes to 4, the time goes to 4, and that like that. So until it gets to 12, until the time gets to 12 seconds. If we plot these values on a graph with velocity on the vertical axis and time on the horizontal axis, we shall obtain We shall obtain a graph as shown in the figure below. If this is plotted, if these values are plotted on a graph with velocity on the vertical axis and time on the horizontal axis, we shall obtain a graph as shown in the figure below. Oh, sorry. Let's look at this. Okay, let's now looking at this. Here is the velocity on the vertical axis and the time on the horizontal axis. Based on information here, the time ranges from 1 to 12 and velocity from 2, 4, 6 to get to 12. As and this slope increases here and becomes uniform and it decreases based on our plot. When this is traced, get this. So now this will be explained later in detail. This is the velocity time graph which depicts the motion of the object during this interval of time. Along OA, which is here, the body is said to be moving with uniform acceleration because its velocity is increasing by equal amounts in equal intervals of time. What does that mean? It states that along OA, the body is said to be moving with uniform acceleration. So when this graph is plotted, let me quickly show you the way or the syntax of how it was plotted. Since we have the radius here already, so we say when when velocity is 0, the time is 0. Okay, the dot is still here. When the velocity is 2, the time is 1. So that's how this is here. When it's 4, the time is 2. When it's so that's how it's plotted until it gets to when the velocity is 2, the time is 11. So like that. She stated that the line OA, the along OA, the body is said to be moving with uniform acceleration, which is here, because its velocity is increasing by equal amounts in equal intervals of time, which implies that when it gets to when the velocity gets to the time it travels increases by 1. When it gets to 4, when the velocity increases by 2, this time increases by 1 as well. When it increases by 2 again, it increases by 1. So it implies that the body is moving with uniform acceleration as stated here. Looking at this again, we have here that uniform acceleration is defined as the motion of an object whose velocity increases by equal amounts in equal intervals of time. However, the small time interval may be. So acceleration along OA, which is the one here, is gotten by the change in velocity over change in time, AD over OD. AD over OD. So the acceleration here is gotten by the change in velocity over change in time. So the change in velocity between these values here. So when it starts from here to here, the change in velocity, which is 10 minus 0, over the change in time, which is 5 minus 0. So the acceleration of the object along OA here is definitely AD over OD, the change in velocity over change in time, which is 10 over 5. Get so now let's proceed. AD over OD is also equal to the gradient of the line OA. AD over OD is also equal to the gradient of the line OA, which is AD over OD, which is the uniform acceleration. OA is also equal to the gradient of the line OA, is also equal to the gradient of the line OA. So you should know that. Hence, acceleration along OA is equal to the gradient of OA from the figure above. This acceleration is 10 over 5, which is equal to 2 meters per second square. Along OAB, along AB here, the body maintains the same velocity over the time interval from 5 to 7 seconds. The body maintains the same velocity over the time interval 5 to 7 seconds, which implies that it is not accelerating because it's not moving. The velocity is not increasing. The body is not accelerating. The body is said to be traveling with uniform or constant velocity because the velocity is uniform over the time interval. The acceleration over this period is 0, the gradient of the line AB is 0. Therefore, the gradient of the line AB here is 0 since the acceleration is 0. So we stated this already. An example of uniform acceleration is the motion of a body falling freely under gravity. Uniform or constant velocity is defined as the velocity of a moving body where equal distances are covered in equal time intervals, however small the time interval may be. Along BC of the figure above, along BC, the velocity decreases uniformly from 10 to 0 over the period from 7 seconds to 12 seconds. So the velocity decreases uniformly from 7 to 12 seconds, which is from year to year. The body is said to experience retardation or deceleration along this line. So that's it. It's said to experience retardation or deceleration along this line. Okay, we stated this already. So uniform acceleration. Uniform deceleration means that the velocity decreases by equal amounts in equal times, no matter how small the times may be. But for uniform acceleration, it increases by equal amounts in equal intervals of time. So in figure 2.1, in the figure above, this deceleration along BC is given by change in velocity or change in time, which is this deceleration here is given by the change in velocity here over the change in time. That's 10 over 12 minus 7, which which gives which gives us 5. So here is the velocity 10 over 5, which gives 2 meter per second square. If an object is thrown up into the air, it undergoes a uniform deceleration of about 10 meter per second square due to gravitational attraction. Retardation or deceleration may be regarded as negative acceleration. A unit like that of acceleration is usually given as meter per second per second. Acceleration may be uniform or variable. It is a vector quantity, that is, it has both magnitude and direction. Now, let's look at distance from velocity time graph. Look at some other things. We will look at some other things before we begin to work on some questions. Consider the velocity. Looking at the distance from velocity time graph. Consider the velocity time graph shown in the figure below. We can obtain the total distance traveled by the object. We can obtain the total distance traveled by the object during the time interval OC, because start here and end here. If the distances traveled during the time intervals OE, ED and DC here are known, during the interval OE, the distance covered is given by this. So what does that imply? We can get the area of you can get the total distance traveled by the object here. By how do we solve a question like that? How do we do that? By obtaining the by getting the area of the shape. How do we obtain the area of the shape? Since this shape here is formed by three shapes, we have the triangle here, the rectangle, and the other triangle here. So we get the area of the first one here, area of the second one, and the area of the third one. Then they are added together to get the total distance traveled. So for the first part of the shape, we have during the interval OE here, the distance covered is given by average velocity times time. Okay, we have that's area of OAE, that's half base 1 over 2 times the base, which is OE, times the height, which is AE. So that's what is written here. During the time interval AD, next one, the object moves with uniform velocity. The distance S covered is given by This distance S2 is given by the area of the rectangle, which is the base times which is length times breadth, which is ED times BD. That is it here. In the time interval DC, distance S3 covered is given by S3, which is equal to half DC base times BD, which is height, which is the area of the triangle BDC. Thus, the total distance covered by the object during the time interval OC is given by S, which will equal to x1 plus x2 plus x3, is equal to the sum of the areas of triangle OAE and the rectangle ABDE and triangle BDC. Total distance covered is given by the area under the velocity time graph. So let's take note of that. The total distance covered is given by the area, so we have to find the total distance covered from the velocity time graph. It is given by the area under the velocity time graph, or the area between the velocity time graph and the time axis. The total distance can also be obtained by finding the area of the trapezium OABC. So this is trapezium. You can also obtain its area from there. This is given by 1/2 open bracket sum of parallel sides, which are these ones, times the height, which is this. So I can actually guess our answer with that. Now let's look at equations of uniformly accelerated motion before we begin solving some questions. The equations of uniformly accelerated motion. We now wish to derive the equations of motion for a body traveling along a straight line with uniform acceleration. The first equation of motion, we have V. So for a body traveling along the straight line with uniform acceleration, which is the velocity increasing with time at the same increasing with time in an interval of time. So the first equation of motion, which is V equals U plus AT, which is the first equation of motion. You need to understand that. So let the initial velocity of a body moving in a straight line be U, yes, its acceleration be A, and the final velocity be V, like the time of motion be T. Then acceleration is given by the change in velocity over time interval, which is V minus U, the final velocity minus initial velocity over the time interval. Then when we solve mathematically, we get this. So we need to understand that V equals U plus AT, which is the first equation of motion, while the second equation of motion is the distance S is equal to the initial velocity times time plus half acceleration times time square, while the third equation of motion, which is V square equals U square plus 2AS. So those are the three equations of motion we have. So these are the equations of motion again. The velocity square equals the initial velocity square plus the 2 times acceleration times distance, where U equals initial velocity, V equals final velocity, T equals time, S distance, and A the uniform acceleration. Also, the distance can also be calculated by the formula here, which is the average velocity times time, which is average 1/2 open bracket the average velocity half open bracket the initial plus final times time, which is also the distance. Now let's take a very quick exercise. A bus traveling at 60 km/h accelerates uniformly at 5 meters per second square. Calculate its velocity after 2 minutes. Bus traveling at 60 km/h accelerates uniformly at 5 meters per second square. Calculate its velocity after 2 minutes. So based on the parameters given, we have the velocity here is travels at 60 km/h, which is the speed, could also be the velocity. Accelerates uniformly at this 5 meters per second square. They have to calculate its velocity after 2 minutes. So based on this, it begins to travel with 60 kilometers per hour. We now have to calculate its velocity after 2 minutes. That implies that we have the initial velocity, then the final velocity. But the unit of velocity is not kilometers per hour, it is a meter per second. So we need to convert this value, the value area, to a value in meter per second. We first change the parameters to the units of meters and seconds, as well as the time, which is a minute. We need to convert it to seconds. So for u, which is 60 kilometers per hour, the formula or the method which can be used to converting unit in kilometer per hour to meter per seconds is multiplying the value. Let's say it's x times 1000 over 60 times 60. So we get the value in x meter per seconds. We get our value x, we get our new value, or rather the new value in meter per seconds. So that's it. That's what is done here. Since we have 60 times 1000 over 3600, which is 60 times 60, which is 50 over 3 meter per seconds. Then the time in 2 minutes, when it's calculated, when it's converted to a value in seconds, it's multiplied by 60. Then you say 2 times 60, it gives 120 seconds. Using the relation v equals u plus at. Now let's begin to calculate. Let's solve for the final velocity, and based on the laws of equations of motion, we learned that there is a formula here which can be used to calculate that. So we have the final velocity equals initial velocity plus uniform acceleration plus time, and we have the initial velocity as 50 over 3 plus the acceleration, which is 5 times the time, which is 2 times 60, which is converted to a value in seconds. So when this is solved mathematically, get 2220 kilometer. Okay, we get 616.7 meter per second. So in order to convert it back to a value in kilometer per hour, what do? We reciprocate. We do 616.7 times 60 times 60 over 1000. So that is it. In order to convert it to a value back in kilometers per hour. When the brakes question 2. When the brakes are applied to a moving car traveling at 60 kilometers per hour, it decelerates at a uniform rate of 5 meters per second square. Calculate the time taken to reach a velocity of 36 kilometers per hour. Firstly, we need to change the unit to the SI unit, which is the systematic international unit. For these ones that are in kilometer per hour, we need to change them to meters per seconds. And for the ones in minutes, change them to seconds. So now let's take the question again. When the brakes are applied to a moving car, let's say, okay, when the brakes are applied to a moving car traveling at 60 kilometers per hour, okay, it's traveling at 60 kilometers per hour, it decelerates at a uniform rate of 5 meters per second square. Now calculate the time taken to reach a velocity of 36 kilometers per hour. We have two velocities, and it begins with 60 kilometers per hour and ends with 36 kilometers per hour. So we have the initial velocity at 60 and the final velocity as 36, but we need to convert them to a value in meter per seconds by using the method stated before. So that is it, we get this, and for the final velocity we get this. So it decelerates at a uniform rate of 5 meters per second square. Deceleration, as stated before earlier, is the negative of acceleration. So when we have 5 meters per second square, 5 meters per second square, because retardation is negative acceleration, so we have a retardation which is a equals minus 5 meters per second square. But how to calculate? We have to calculate the time taken to reach a velocity of 36 kilometers per hour. So you can actually mix up this formula to do that. So since we know the remaining values, it sets the time taken. Then you do this and get the final answer. Question 3. A car accelerates uniformly at a rate of 10 meters per second square from an initial velocity of 36 kilometers per hour for 30 seconds. Find the distance covered during this period. We have to find the distance covered. You should know that the first formula we'll be using will not work for it. So based on the data given, we have that the car accelerates uniformly at a rate of 10 meters per second square. We have the acceleration as 10 meters per second square from an initial velocity of 36 kilometers per hour. So this needs to be converted to a value in meter per second for 30 seconds. Okay, it accelerates uniformly at the rate of this from an initial velocity for 30 seconds. Find the distance covered during this period. So we have this, and this, and we have to find the distance covered. We can actually make use of this formula among the laws of the equations of motion, which is distance equals initial velocity times time plus half the uniform acceleration times time squared. We have this, then you get the final answer. So now let's look at the velocity time graph. Let's look at the velocity time graph. Okay, a bus moves from west with a uniform acceleration of 2 meters per second square for the first 10 seconds. Now this is the velocity time graph. So here, let's construct the diagram here. Since we have that this will be the velocity on the vertical axis and the time on the horizontal axis. Okay, so now we have this here. We have the velocity and the time. This in meter per seconds. This in seconds. So what's the question here? The bus moves from west with a uniform acceleration of 2 meters per second square for the first 10 seconds. For the first 10 seconds. I think I need to extend the line. This seems like a little line. Okay, let's even, oh sorry. Now we have this here. Here, like yes, this, oh no, like this. Okay, like this. Now let's make use of this line here. So we have the velocity here on the vertical axis and the time in seconds on the horizontal axis. So it moves with a uniform acceleration of 2 meters per second square for the first 10 seconds. So let's say it starts from west, which implies that it begins from times 0, and it moves for the first 10 seconds. So for about, we need to understand the question. It moves from west with a uniform acceleration of 2 meters per second square for the first 10 seconds. So here it is with a uniform acceleration. I've been told that the value here on this part is the uniform acceleration, like this, for the first 10 seconds. So let's stop here, which implies that this, from this point to this point, 10 seconds, because that's the time, and here is the uniform acceleration of about 10 meter 2 meter per second square. Now it then accelerates at a uniform rate of 1 meter per second square for another 15 seconds. So it accelerates again for of 1 meter per second square for another 15 seconds. So what do we do? So now we need to increase it here like this for another 15 seconds. So here let's make it like this. What's the length here again? For another 15 over, okay, 1 meter per second square. So we need to be conscious of the lines. This must be longer than this because here is our 2 meters meter per second and 1. So now let's take the line downwards here for about 15 centimeters again. After that, 15 seconds rather, or is that right? Or 5 seconds. Okay, then accelerate at the uniform rate of 1 meter per second for another 15 seconds. We don't write 50 seconds since it's accelerated for another 15 seconds. Then we add 15 seconds to 10 in order to get the time here, which gives us 25. So therefore, well, to get the value between this, we need to subtract this, then we'll get the 15 seconds actually. It continues at a constant speed for 70 seconds. So let's take that. It continues at a constant speed, and we've learned that it implies that it's not accelerating at a constant speed like this based on our explanations earlier for about 90 seconds. Oh, sorry. Okay, let's make it like this. For about, is it 90 seconds? For 70 seconds rather. Okay, 70 seconds. So we have 70 here. We need to add 70 plus 25. This gives 95. So I think I need to increase the line here. So allow me to do that. So now that is it for about 70 seconds. Then once again, and finally comes to rest in 20 seconds by uniform deceleration. In 20 seconds, it comes to rest. So that implies that after 20 seconds, it came to rest by a uniform deceleration. Then what happens? We had 20 to 95. It gives us 115. 115. So we have the t here in seconds. So we are getting there. Now draw the velocity time graph of the motion using the information given above. From your graph or otherwise, calculate the total distance traveled. So now let's label our diagram well. Now based on the information given here, we stated that a bus moves from west with a uniform acceleration of 2 meters per second square. So now let's include that here. For 10 seconds, which is the first one here, we have 2 meters per second square. 2 meters per seconds, or let's need to write this clearly. So yes, for 2 meters per second square. Okay, okay, it then accelerates at a uniform rate of 1 meter per second square for another 15 seconds. Okay, it accelerates for another 1 meter per second square for another 15 seconds. Okay, so we have about 15 seconds here, which is the one, when this is subtracted, the time between these 15 seconds, and we have 10 seconds here. Okay, I think I need to use a different color for this ones here. We have 15 seconds here. Oh, I need to maybe change the color. Sorry for that. Okay, this is appropriate. 15 seconds, and we have 10 seconds here. So it continues at a constant speed for 70 seconds. Okay, it continues at a constant speed. So that means the speed, the time taken between these two, yes, 70 seconds. By uniform deceleration, and finally comes to rest in 20 seconds by uniform deceleration. So it comes to rest by 20 seconds by uniform deceleration, which is down here. Draw the velocity time graph of the motion using this and calculate the total distance traveled. Now let's label our diagram. You can choose this to be AO, this to be B, C, the what else do we have? Let's check this part. Okay, we have G, F, and E here, and A. So let's do that as well. Okay, let's take it out. G, F, and E. We have G here. Let me use the red pen. Let's differentiate it well. We have G, F, E, and A. Sorry. So now let's proceed. We need to include. Okay, now calculate the total distance traveled. So we had calculate the total distance traveled. As stated earlier, we learned that the total distance traveled under the velocity time graph is the area of the shape, is the area of the shape. So what which implies that we need to obtain the area of each of them, then add them up together. Since this is not a trapezium, so we cannot really do that for that unless we break them, we solve it gradually. So in a nutshell, we need to get the area of each of them, then add them together. So how do we solve a question like that? So that indicates that for getting the area of OGA, which is the triangle here, what needs to be done? And the formula for doing that is the base times height, which is half base times z. Since we have the base as 10 already, the area of the triangle, we don't know the height. We don't know the value of the height. So how do we get that? So that indicates that we need to even get the value of the height, which is known as the velocity in the time graph here, which is the velocity here, the increment here. So how do we get that? Since it is stated here that the uniform acceleration uniform let's use a white pen. It is stated that the uniform acceleration is let's take for OAG. It stated that uniform acceleration is let me write that here. OAG, uniform acceleration is 2 meters per second square, and the time taken is 10 years. So we can obtain the value of the velocity by saying, which is the velocity v, by using the formula of the first equation of motion, which is v equals u plus at, then we say v, which is equal to u, which is the initial velocity. Since it stated that the body starts from west, they start from velocity 0. That's what it indicates. It starts from velocity 0. U plus a, which is the uniform acceleration of 2 times time, which is 10 seconds. So what do we get? We get 20 meters per seconds, which indicates that the height of this one here is 20. So we can actually do this. Let's differentiate it to say that's 30 meters per seconds. Now we can let's get for this one as well. It's stated that this accelerates for about 1 meter per second in 15 seconds. So for A, the GE, to get the velocity, we say we have data given for A, the GE, the uniform acceleration is equal to what is it? Okay, this is here 1 meter per second square. One, no, sorry, the time given is okay, ranges from this that's 15 seconds. It moves for about 15 seconds. 15. So what's given here again? So we need to get the velocity, which is the final velocity. Okay, now based on what we have here, since we have the formula v equals u plus at, we find out that u here indicates the initial velocity. So for this one here, the final velocity is the one we are finding, while the initial velocity is still unknown as well. But we cannot have two unknowns in an equation, so we need to get either of them, then solve for the other one. So since we are actually finding the final velocity, which is the height here, so what's the initial velocity in order to solve the question? Initial velocity should be here, should be where it starts from here, and where is the final velocity, where it ends. So how do we solve it? It's already given in the question. Initial for OAG, we discovered that initial velocity is 0, but for BF, the initial velocity is 30, because looking at this, the velocity here starts from 30, then ranges to this point. So we need to understand that. So this is the velocity for ABGE. The initial velocity is 30. So we now solve. We say V equals U plus 80, which is initial velocity, which is 30, plus 1 times 15. Say 30 plus 15, which gives us 45 meter per seconds. So here is the velocity of this air, which is 45. So uh before we proceed, I just realized something. We got 20 here as the velocity, so that should be included here. It's not 20, so that's why we are having the error. So it's not 30, so this needs to be erased, as this is 20. So what needs to be done now? For this, the initial velocity is going to be 20. Let's It's going to be changed to 20. This should be changed to 20, and this is not going to be the final answer. So now let's do that right now. Since we have this as 20, initial velocity here will be 20. So we have 20 plus 15, which should be given which should be 35 meter per seconds. So that is the final velocity, which is 35 meter per seconds. So now the final velocity here, since initial is 20 and we got the final velocity as 35 meter per seconds here. So what's necessary to be gotten again? So now we cannot obtain the area of this, since we know the height already, which is 20, and we know the height of this one already. For this one here, we have the area of the rectangle, which is length times breadth. That's 70 times the height here. Okay, we have the height here already, so they are already the same. And for this one as well. Okay, so we've gotten the final answer. Now let's begin to solve. Now allow me erase this ones here. Okay, now for the area of OAG, let's get that first, which is distance 1, s1 equals half times base, which is 10 here, times the height here, which is 20. Then we got this this 10, and 10 to 10 gives 100. You have 100 meter for the first one. For s2, which is which is AGFB. So that's gotten here by making use of the area of a trapezoid. Or is that was not here? Looking at this one here, we have this. Okay, Yes. So that's got AGFB should be gotten because look at the shape. The shape looks like a trapezium. Yeah, yeah, yeah. So we need to get the area by finding the area of the trapezium, which is half 1 over 2 open bracket the area of the sum of the parallel sides times the height. So 1 over 2 plus the sum of the parallel sides. These are the sides here. 1, 2. So we have this length, this one here, the length of this one. So this parallelogram can be drawn out like this. So we should figure it. Uh, so this is it. So we have A here, we have G, we have F, and we have B. We need to be able to identify it well. So AB, which not AB, no. Sorry, we have this ones here. We have A here, we have B here, we have F here, and then we have G here. So now for AG, the length of AG should be 20 as we've got it here. So you write that here 20 plus the other length here, which is this one here, FB, which is has gotten here, which is 35 times the height. So where is the height? The height is the one here. So looking at this now, we can actually get the height, or let's look at it for the height of this lift. So sorry, let me take it back to the open software I'm using. So now where are we? We stop. Okay, we stopped at this point here. So we have 20 plus 35 times the height of the trapezium, which is the one here, which is the height here. So how do we get the height here? Okay, since it's already here, looking at this one, we have the height here. It's also the line here. They are equal. The height here, the line here, and the line here are equal to, and this is already 15 seconds. So we get 15 here. So that's how we get the value. We say 1 over 2 times 20 plus 35, that's 55, times 15. So when this is solved mathematically, we get 412.5 meters. 412.5 meters. So now let's solve for S3. So for S3, which is the one here, the area is the breadth, length times breadth. Length is 70 seconds already, which is 70 times breadth, which is 1 here, that's 35. The one here, that's 70 times 35. 70 times 35. And based on the answer here, we have where is it? 2450 meters. 2450 meters. And the last one here, get the area of the triangle by saying half base times height. The base is 20, while the height is the height of this one, which is also this one here, which is that is 35. So oh sorry, that's the height of, okay, for S4 now, 1 over 2 times the base, which is 20, times the height here, that's 35. So for this, for S4 we have 350 meters. 350 meters. Okay, so now how do we get the total distance? The total distance, that's the area of the the curve under the graph, the area of the graph, which is this plus this plus this plus this, that's 100 first year plus 412.5, then plus 50, that's 100 plus, let's start from 350 here again, plus I make sure I add each of them. So you have 350 here, for h3 2450, let's include it. Then we have 412.45, is 4505. Okay, then we have 100. So when we solve this, get 3.3125, 3.3125. So now that's the total distance traveled, that's the answer for that. So we have to calculate the average speed for the whole journey. So since we know the average speed is the distance over time, so we get it, since we've gotten the distance already, we divide it by the total time taken throughout the journey, which is from 0 to 115 here. So then we say distance, the average speed is equal to distance over time. It's 28.8 kilometers per hour. The average retardation as the body is brought to rest. Average retardation as the body is brought to rest. So how do we get that? We say CE over ED. So based on what we have here, we have CE over ED, which is the retardation of the retardation we have to find is CD here. So average retardation as the body is brought to rest. So how do we get it? We find the velocity over the time, which is also the formula for acceleration, is velocity over time. So velocity here, as we've gotten before, is 35 over the time, which is 20 years. So that's how it's gotten. Then we say 1.75 meters per second, which is the retardation along CD. Then the maximum speed attained during the motion. What's the maximum speed? You need to understand that. That's the velocity. And based on what we have here, the maximum speed attained is 35. There is no velocity higher than 35. So that's actually 35 meters per second as already calculated. So thank you very much for watching. So goodbye. Thank you very much for watching.